Okay, here are just a few more examples of Lenz's law then. Okay, so here again we have a wire, current's heading up. Probably should have it head down every once in a while. But if it's heading up and we move this hoop to the right, if we move it that way, then what's going to happen to the current in here? Will it go left or right? Remember, Faraday's law will tell us how much current we'll have if you know, say, the resistance of the wire, because then you could use Ohm's law. To get the current, you would just use E over R, and to get E, you'd use Faraday's law. But let's just concentrate right now on applying Lenz's law. So right now I have a field that's going into the paper, and so at least on this side it is. It's strong, close to the wire. It's coming out of the paper here. But then as you go out, it gets less and less and less and less. And so if I move this way, that means I'm getting less x's. And so if I'm getting less x's that way, when I move it that way, then what that means when I'm moving it this way, if I'm getting less x's, that means that it's going to try and make its own x's because it doesn't want the x's to change. And to make its own x's, it's going to have a field that that's going to go this way. You see how the current heading clockwise gives me more x's? Now, I probably should have told you this in the last one, but you know, the Lenz's law is about how this hoop tries to stop the magnetic field inside it from changing, but it always loses. Just like mass, when you put a force on it, it's going to change its velocity. It may try to resist the change in velocity, but it's not going to win that battle. You put a net force on an object, it's going to accelerate. It's just that it's going to try and resist. Same thing with this. So it's going to try and resist by inducing its own field inside, but it's not going to win. Okay. Okay. Next one. Let's say now these can get a little bit more interesting. So let's take a look. We got a coil here, and if I'm going to move this magnet up. So I'm going to move this magnet away. Now I want to know which way the current's going to flow in this resistor. Will it flow up or down in the resistor? Okay, well, let's take a look at the field. The field from a bar magnet loops around like this, and it goes like that. It's pointing like that. And so that's pointing down there. Those are down arrows. And it keeps going like that. But if I move this up, do you see how the magnetic field in there is getting less? It's going down. The magnetic field's going down from that bar magnet. And it's getting less. I'll say that one more time. The magnetic field from this bar magnet is actually down. If I put a compass here, it would point down. But as this magnet moves away, the actual strength of the field is getting less. So this is going to try and make its own field down. And so to make its own field down, I take my right hand and I curl my fingers. And to get that field to go down inside, I'm thinking that the current has to go this way. Doesn't that give me a downward field? It sure does. Excuse me. And so that means that the current is going to be going like this. It's going down through this resistor. Okay? Let's try another one. Come on over here. I wish I could zoom in with this thing, and probably will eventually learn how to do that. I mean, I know this can zoom, but I don't know that it's worth it. Okay, so we have a battery, a switch that's open, and here's a solenoid, and you know that when I close the solenoid, I'm going to induce there's going to be a magnetic field that is inside that solenoid. And that field will interact with the second solenoid, and so that's going to induce a current in here. And so which way will the current go in this resistor, up or down? That's a little resistor there. Okay, So let's figure it out. If I close this at t equals 0, there is no current, but then like right away, well, real soon after, there's going to be a current flowing like this. And so that's going to make a field. If I put my fingers like that, it's going to make a field up. Keep putting my magnetic fields in red. So that's going to make a field up like this. It will circle around. Fields always circle in on themselves. They're always closed loops. So that's going to make a field up. And that field is going to interact with this one. So this didn't used to have a field inside it. And then all of a sudden there's this upward field inside this top one. So this is going to try and resist that by making its own field that's down. Now to make a field that's down, then I'm going to take my fingers and curl them in the direction that I want. I like my thumb to point down. And so if I curl my fingers that way, apparently that will give me a down. Yeah, if they go this way, that's going to give me a downward magnetic field inside. And it's only inside that matters. So that means it's going to loop this way and come up. And then that way. Okay, another one. Okay, now we have this piece of wire that's like that. And I'm going to put the field going into the page. We can say it's a uniform magnetic field. And we're going to move the bar to the right. Okay, now if we move the bar to the right, then what's going to happen is this is our hoop. This is the hoop that's a closed hoop. This bar is metal. And as it moves to the right, won't there be more X's being added? There sure will be. There'll be X's being added. So this will try and make its own dots. And to make its own dots, to negate the changing X's are increasing. That's flux. So to make its own, it's going to make its own dots that will negate some of that. And so to make dots, it's going to have to go this way. So that means the current will go like that, like that, like that. See how that gives me some dots in there? Okay. Now I'd like to take a closer look at this because with this one, if this is heading this way, and you remember we had some X's, there are the X's, and I want to show you that this is consistent with what we already know about charges. So let's say that we were going to follow the electrons, the flow of electrons. Now we've already said that it's going to make a current this way. Let's see, we're adding X's, so it's going to try and make its own dots. So we said it's going to make a current this way. But there's another way we could get that. If we think of electrons being in this wire, there's some electrons there, and if they're moving that way across this field, won't they get pushed down? Yeah, because the field is down, and they're moving this way. I'm using my left hand. So they'll get pushed this way. Now, if electrons get pushed that way, that means that the flow of conventional current is the other way. The flow of conventional current is the flow of positive charge. So it's consistent with what we thought it would be. Okay. One more example of that, how you can get this without Lenz's law, is not always. You can't always do it without Lenz's law, but a lot of times you can. You remember this one? Wire, hoop. There's X's here. That die off, and if you move it to the right, what happens when you move this to the right is it's dropping off X's, so it's going to try and make its own X's, so it's going to push a current this way. It's losing X's, and to make its own X's, it pushes it that way. But there's another way to look at this, and I'm out of time to tell you. But it has to do with what, well, I'll tell you another time. Okay, bye.